Sveikas,
Hello, everybody.
Sveiki. Hello.
Hello, everybody. Welcome to our Lithuania's Artificial Intelligence Association meetup. Today, we are going to talk about causal inference. And this is actually a super exciting topic. I really love that we are having two amazing guests today, Evgeny and Povilas, from both from Lithuania's AI Association. So let me start with a quick introduction. My name is Dovydas. I am the president of the AI Association. I'm also machine learning team lead at Vinted, and I'm also a data science lead at Turing College. Give me a second, I need to fix some resonance. Yep, hopefully this is going to be a little bit better. Let me move to the our today's topics. So first of all, we are going to start with some community updates. Then we are going to see Evgeny's presentation, what machine learning and deep learning does not know. And after this presentation, we'll have Povilas' presentation, some causal inference approaches. Finally, we'll have a panel discussion with both of the speakers. There, we are going to, you'll be able to ask their questions and see if that's, of course, get answers to your questions. So again, super excited because causal inference is this amazing, interesting topic, which we haven't covered yet in our meetings. And I'm super excited that we are finally getting this topic in our meeting. So let's start with the community updates. We have a few things which I want to celebrate. So first of all, we had a successful visuotinis narių susirinkimas, or general members meeting last month. It went pretty great, and we discussed, we presented the OKRs for the next quarter. We also reviewed the last quarter's OKRs and just in general identified what we want to do as an association. Then we have also created a dedicated Slack just for Artificial Intelligence Association members. So this finally we have a place where we can collaborate, which doesn't have like a limited message space or any other problems. We can just have the full history for all of our projects. We're like, some of you might be thinking, okay, so are we like stopping the current Slack? It's gonna be available for everybody, for all machine learning enthusiasts in Lithuania, and we'll have just a separate Slack for the members and the projects which we are doing. So very excited about that, and yeah, again, this tool is really gonna help us to like do more. Also want to point out that our website is constantly being updated. So even if you have been to our website, yep, sorry about that. Even if you have been to our website like a long time ago, it was not super functional, but now we have increasingly number of interesting things there. We have our projects, we have our OKRs, we have even vocabulary, how to translate Lithuanian terms or English machine learning terms to Lithuanian terms, powered actually by Linas, again, a member of our association. And we have like a lot of amazing functionality and some more in the works as well. So that's that's the main gist of what we have to share as a community. Now I'm very excited again to introduce Evgeny. Evgeny is machine learning team lead at Vinted, and today he's gonna present us with what machine learning and deep learning does not know. Give me a second to. Yep, Evgeny, floor is yours.
All right. Can you hear me?
Very well.
Okay. All right. So I'm gonna start sharing my screen. And tell me if you can see in the slide mode.
Not yet. Yeah. Now it's very yeah. It's in the slide mode now.
Right.
By the way, if you have any questions for Evgeny during the presentation, let them ask. You can ask them in our YouTube chat. I'm going to be monitoring the chat and forwarding questions to Evgeny.
All right, excellent. Thank you, Dovydas. So I'm going to kind of motivate today the topic of causal inference. I am not going to introduce the methods of causal inference in this particular presentation, but the goal of this presentation is to motivate why you might be interested in the causal inference topic, to motivate Povila's talk, and show in which kind of cases in my past experience you might want to start thinking about causal inference. And particularly, I want to motivate the question of causal inference by asking what ML or deep learning does not know. So that is the subject of this talk. To briefly start what my ML journey has been to connect, I'm Jeff Gamper. Mostly you can find me on Twitter. And I've been working in ML maybe since 2017. First I was swimming, then I went to study to the US, and then I started my master's at Warwick. And there for my master's, we worked on the machine learning for exoplanet detection, and then also worked on histology images for my PhD, and then did some machine learning with climate data. And now I'm working with machine learning at Vinted and of course, Lithuanian AI Association. But I'm primarily going to motivate today's presentation with my past experience in histology. This is the field of medical imaging. And let's start by first asking, what is the strength of deep learning? We see that there are plenty of papers published every day on arXiv on deep learning can do this, deep learning can do that, deep learning can do speech recognition, deep learning can do image classification, natural language processing. But what is the real strength that ties together all these different applications of deep learning? And to kind of motivate what that strength is, I would like to briefly show a demo of what I think that strength is. So I'm going to quickly pull up a Jupyter notebook here and show a very simple example. And that very simple example is right here. Let's generate that data. So some of you might be familiar with this example from Chris Ola's blog post from Google Brain, and never do live demo because now it doesn't fit on the screen. But anyway, we have this simple data set of two circles, the red circle and the blue circle, and we just want to classify between the two circles. And as most of you would know, this is not something that you can solve by logistic regression unless you do some feature engineering. It's not linearly separable, but this example very well demonstrates how deep learning is a very powerful tool nowadays that allows you to approximate any sort of functions and separate any sort of data. If you make the network sufficiently deep. So here you can see we are working. Oh my God, we're working again with this data set. It's the same two circles, blue and red circle before, but here we are working with linear model, trying to separate it with a straight line. And it's not sufficiently deep network yet. It's not sufficiently parameterized. So what happens is that because we're working with matrix transformations, it's just trying to stretch the space. It's trying to kind of squeeze the red circle, the red data on the one side, blue data on the other side, but it can't really do that. It can't transform the space sufficiently yet. But if we stop this process for a second and we change our model to a larger dimension, increase the number of parameters, and then we rerun the whole thing. We will see that by adding extra parameters, by increasing the parameterization of our models, our model can efficiently find an extra dimension, expand the space into an extra dimension, and then squeeze the blue and red on the either sides of the straight line. And that very well demonstrates the power of deep learning that connects speech recognition that translate natural language processing and the image processing. Is that provided that we have a well-defined objective function, provided we have a well-defined objective function, provided we have x and the y that we are mapping to, then we have a very, very strong method, essentially a very powerful function like this muscular dodge that can learn a mapping from any x to any output f of x. And that's something that is very, makes deep learning very powerful, but that's something that also should make us very conscious. And this is the primary kind of goal that I will primary way that I will try to motivate why you might want to start to think about causal inference when you work with deep learning and when you have these powerful functions. So I will do that by demonstrating a case study, a few examples from histology, medical imaging field, where deep learning has been applied over the past several years, since 2014. So histology is a field of medical imaging where you work with very large images like you see here. These are usually 100,000 pixels by 100,000 pixels or more. So these are not the kind of images you would work with ImageNet or CFAR. You can't fit them into your memory. You have to split them into sub-images. And before we go into the technical details of that, let me motivate why you work with these images in the first place. So the reason you work with these images is to diagnose cancer or any other sort of disease that might be suspected of in the that we might be suspecting to see in the patient. So the way these images are produced is that a surgeon will take a tissue sample from the patient, you see on the left here, then they will stain it, apply colors to it, slice it, and then put it into a specialized scanner that then will scan these images and will get something that we see on the bottom right. These are pink or other type of color, depending on the stain images, within which doctors will try to see patterns to diagnose cancer or any other sort of disease. And these are the type of images that we've been working over the past several years. And I will tell you the story of histology, the kind of steps that the whole field has been going through and why causal inference suddenly becomes important. So to recap, the histology images are very large. So if you look at this grid of squares, this is kind of just to illustrate, the images themselves are 100,000 by 100,000 pixels. So what we often have to do is to break these images into smaller patches and then process each individual patch with a convolutional neural network and then aggregate those predictions. So you can see that small f of theta is a convolutional neural network that we apply per patch. And then large capital F is maybe some sort of function aggregator that aggregates the representations coming from a convolutional neural net. But we'll get to that. This is just kind of to demonstrate the abstract way of thinking about the problem of histology. And Dovydas, let me know if there are questions popping up in YouTube. If I'm rushing too fast, let me know.
Yeah, just a comment that it was a beautiful demo. Yeah.
Awesome, thank you. So this is not my demo. I just stole it from Chris Holler from Google Brain. He published it a long time ago. I just coded it up in PyTorch because he never released his code when I was in my master's, and that was really frustrating. So always open source your code. That's the lesson. But anyway, and on the right, this is sort of plate diagram from Bayesian statistics to represent the whole process. That usually we have a bag of images BI, which is the whole slide image. And then we have patches of images XJ. And we can assign some label to the XJ patches. It's a small y. And there is also usually the actual label we care for is capital Y, which is is there cancer in this image or is there no cancer? But because we can't fit the whole image into the memory, we have to split them into small x's and learn some sort of label for small x's and then aggregate that across the whole image. But we'll get to that. So let's start with where the field was in 2016. In 2016, what people were doing is precisely that. They will take the small patch of an image, as you see here, or in section E or section G or C. And then for these patch of images, they will then learn a label, or like here, background, adipose tissue, mucosal glands, debris, immune, stroma, or tumor. And by the way, these are still larger sub-images. Actually, in the original work, this image is broken down into further smaller images of 224 by 224 patches. And then these are just the aggregated results of that, the color maps that you see here. So actually, the actual patches are smaller. And we just apply CNN to all of these patches. And this kind of is still fine. We see that by breaking down into patches, the neural network picks up different structures. It picks up that there is a tumor here. It picks up that the green here is a stromal tissue, et cetera, et cetera. That's where the field was a few years ago. Then naturally, we might want to expand to pixel-based tasks, segmentation, semantic segmentation, or instance segmentation, where we want to detect particular objects within the image patches. So here, if you look at the colon tissue, we want to look at the colon glands, and these are important, and also diagnosing different subcancer types, etc. So researchers have been working on models that can segment different glands, as you see, as I've illustrated here. So this is the kind of work that we worked in the past as well. Propose different networks that would distinguish these glands and segment them. But we're still working at the patch level. We're not aggregating anything yet. We have to, this is a painful process to produce these labels, produce these data sets, because we'd actually have to have doctors who would then go and annotate every individual glands or label every individual patch saying that this is tumor, this is not tumor, this is stroma, this is not stroma, this is gland, this is not gland, etc. So this is quite a laborious task. Naturally, we can then go to a more granular level, and you can start segmenting nuclei and classifying individual nuclei in the tissue. So this is an example of doing instance classification for nuclei. This is particular work that we worked on, not solving the segmentation task, but actually efficiently producing the data sets for segmentation, where we'd have human in the loop. But that's all kind of still conceptually understandable tasks, where we know what is a nuclei, where we know what is a gland, we can point fingers at it, we can point at the tumor, doctors know what these things are. And then, as I've talked about, once we do it at the patch level, we detect all the nuclei here on the right. Then we can zoom out and look at the larger images, larger field of view. And then we can look at the whole slide image, as you see in the middle, first row and the second row. These are whole slide images. And then we would aggregate in some way these spatial information of nuclei classification in the whole slide image. And then we would do it for some summary statistics. And then we could fit, for example, a random forest on top of it and produce a label of the whole slide image. Is there tumor in this whole slide image? Is there no tumor? Is this invasive cancer? Is it not invasive cancer, etc.? But we go through these different stages of hierarchy, where we work at patch level, then at aggregate level of whole slide image, and we predict the final label that we care for. And so on the kind of recap, but the actual label that we care for is the classification of the whole slide image, not the individual patch within it, but the whole slide image, because these are what our medical records in. This is how doctors think. They classify whole slide image, they classify the whole case of a patient. And we kind of engineered that step in between, where we have XJs and YJs for which we assign the label and we train the models for, and then we aggregate them to do the prediction of the whole slide image. And this is purely out of computational reasons. But what happened not so long ago, what started to happen in 2019, as people started to increase the number of GPUs available, people started to skip the task where we would create the data set halfway through, where we would label every individual patch, and they would actually train the whole system end to end. They would train both F small as well as F capital. And they would that way kind of sidestep the whole idea of collecting data for the patch level. And they would train directly on the labels of the whole slide image. And since then, the field has just taken off in trying, because then we suddenly don't just have tasks like cancer, non-cancer, we can predict survival, we can predict all sorts of other things that I'm going to talk about in a few seconds. People then have started to improve the architectures of the deep neural networks that are used for this multiple instance type learning, where we have patches for the whole slide image, then we have attention over all the patches in the whole slide image, and then we try to predict what's going on the whole slide image level. But up to this point, the label Y was human observable. We can say, this is cancer, this is not cancer, this is gland, or this is not gland, or this is nuclei, and this is not nuclei, and what kind of nuclei they are. We could visually validate these labels and say, yes, this prediction makes sense. But as I've told you, for patients, you have all sorts of other labels, other data that you can try to predict from whole slide image. Because now you have this end-to-end system. You just take the data from the hospital and you see what you can do. And you can see that visual here, that these labels are possible to validate. We have adipose, and you can see that these are clearly distinguished features of adipose fat tissue here on the top row. You can see mucosal in the middle row, and that sort of makes sense. Or lymphocytes, you can see that these are just a collection of lymphocytes. These are patterns that doctors themselves can recognize. And hopefully I'm making sense here where I'm getting to, or you'll see in a second. But what happened more recently is that labels have started to become less human observable or human understandable. So suddenly, because we have patient data, we can start to predict molecular information, genetic mutations that we got from genetic tests, or metastasis origin. And this is what we started to see in the field. So people started to take this cell prediction, for example, at the patch level, and then aggregating that and then predicting, for example, treatment relevant predictions like molecular information, et cetera, which is not really human understandable. It's purely done because we have that powerful function approximator like deep neural network. And we just have the data from past genetic tests like genetic mutation, molecular information, and we try to learn the mapping from an image to molecular information. So here, for example, is a paper from last year from Jacob Nicholas Cather, where they've tried to predict from whole slide image different genetic alterations that are important for the chemotherapy assignments. And the way that it's important to understand how this data has been generated. Essentially, you have patients, whole slide images for these patients, and you have other clinical tests that have been done for these patients. And these are clinical tests for genetic alterations are very expensive, and they are done through different machinery. And then researchers ask questions, can we actually infer the results of these genetic tests from the whole slide image that is way cheaper to produce? And actually, the researchers just went ahead and tried that, and they see that you actually can predict where and which tissue regions corresponds to specific genetic mutations. And it is not something that doctors can do. And that's why I mean that these labels and predictions become less human understandable, less human observable. And you see how they process it here. They then try to do all sorts of other predictions like expression of different genes, survival from an image, et cetera, et cetera. And there were multiple papers that have been coming out who do very similar things, just with slightly different applications. And the arguments that they make is that there is some difference in the mutations, a visual difference in the mutations, that apparently if you cluster this based on the deep neural network that you train to predict these labels, then you can then cluster these images and see that there are slight differences between them. But we don't know the mechanism behind the label generation. And that becomes really important. And that's where causal inference starts to slowly appear. So here's another example where we don't know the labels. This is a bit more complicated example. Here we have a cancer that originated in breast, and then cancer can then travel to other tissues, to other organs, and then develop there. And we call that those cancers metastatic. And what these researchers were trying to do, given that patient's data where they have determined if it's metastasis or not metastasis, what is the origin of that cancer and where that cancer is based, they try to predict, looking at the tissue, what is the origin of that cancer? Has it metastasized, and where it has metastasized from? So this is, again, something that doctors are not able to do. This is done purely from the clinical data that is available within hospitals. And it's not something that doctors can explain themselves because there is no clear visual information in an image. And there's another example from colon metastasizing to liver, lung, or lymph nodes. And this is also a very recent paper from last year. And this is just another example of an architecture where they tried to do this sort of prediction of predicting metastasis, where they have clinical data. They have, for example, a colorectal host light image. They know the gender of the patient. They know if it was a primary cancer or if it was a metastatic cancer. And then at the output of the neural network in this multiple instance learning setup, they predict if it was a primary or metastatic and where it came from, primary prediction. So these are kind of, it's all done from the clinical data that is available within hospitals, but it's something that doctors cannot do and something that doctors cannot see within an image. So then the question is, what is the danger of these methods? What is the danger of us trying to predict these labels that we are not aware of, that we don't know the generating process for? And here we can motivate it with a simple example here. And unfortunately, can't engage with an audience, but here's an example of a supervised learning problem where we have data for genotype, for phenotype A and B. And we see there is a linear relationship between the activity of either genes B or A and the phenotype. And the question is, if we set activity of gene A or B to 0, so either here or here, then what would be the value that our supervised learning model would predict at that particular level of gene activity, at 0? And if our model is a deep neural network, and here it's a simplified example of a linear regression, it would learn a straight line here, right? It would learn a straight line in both ways. So naturally, it would predict then at the activity of gene A or B at 0 will be also 0. And that's purely inferring from the correlation in the data that we've acquired. Just the same way as we acquired clinical data on the relationship between image and a certain molecular composition within that patient's tumor. But actually, this problem is very much dependent on the causal structure. So if there is a direct relationship between gene A and phenotype, then indeed we can expect that the activity of gene A at 0 would imply a phenotype of activity around 0. But if we see that there is a common confounder between the gene B and phenotype, then actually that linear relationship will only be a result of a correlation between the gene B and phenotype through a confounder. And if we set the activity of gene B at 0, then the phenotype should not change in the actually. And that's where this is to motivate. This is to motivate the examples we were looking at predicting the mutation type from the image, right? If we know that mutation types cause certain patterns that we observe in the image, then it's a fine task to do. But the point is that these research papers and these results are published without us knowing the underlying causal structure. And then we cannot always be certain that we are doing the correct prediction here, because there could also be an unknown confounder that causes the mutation type, as well as causes a specific patterns that we observe in an image. And that's when we have these very powerful models and we apply it to observational data that we see in clinical data in hospitals. It's an observational type of data. It's not experimental data. We run into the risk of exposing ourselves through these powerful models to the unknown confounders that might appear there. And we actually inferring correlation, not causation, using our powerful models. Hopefully I'm making myself clear. I don't know if there were any questions appearing, Dovydas.
Yeah, just a few questions, but I think they would be best left for the end.
Okay, sounds good. All right. So kind of, hopefully that was a good motivation to what will be talked later on. But through these examples, you can see that we can't rely just on these powerful models. We have to also understand the underlying data generating process. What was it that made our labels the way they are and made our data the way we are? And this requires us to think about causality. It has the implications to model predictions and how reliable they are. And also it often means that we have to be explicit about it and think about the underlying AI ethics. So that was the motivation for causal thinking. Hopefully I didn't run over time.
Right. Thank you, Evgeny. We'll tackle some questions right now. I also want to ask the audience if you like, let's wait for the other presentation, and then both Povilas and Evgeny can jointly answer your questions in the panel discussion. But of course, like the current questions which are for Evgeny, I'm gonna ask him right now. So the first question is what you mentioned, that you always publish your code. Where can we find your Jupyter notebook?
Oh, it's not published. Very good point. I'm glad that you caught that.
Right. I guess like we'll try to work it out and publish it together with the recording of this.
Yeah, we can do that, definitely.
All right. Then Tadas asks, hi, it is a very interesting theme. I would like to ask if model building consists of only one particular disease, or it can be extended to a wide range of diseases.
This is an excellent question. This is something that most of my PhD was about, because I remember there was a meeting with the partners in the hospital, and we just received an NVIDIA DGX machine in our lab, and we needed to come up with a cool project to show that let's use all of the 18 GPUs that are available there. So naturally we thought, okay, let's just chuck in all the possible diseases there, all the possible labels that we can predict, and start from there. And actually this kind of idea is very contradictory to medical domain experts, because they are like, no, how can you predict at the same time a tumor, non-tumor, and also segment nuclei, or doing tumor, non-tumor detection in colon tissue, but also doing it at the same time in lymph nodes? These are just two different things and require two different doctors to do. But then if you think about ImageNet and classification of 1,000 labels there, you classify turtles and airplanes in the same data set. So for neural network, it doesn't really matter. It's a powerful function approximator, so you just throw the data set to it and it does the job. So in that sense, if you have the data and you have the function to do that, deep neural network, you can classify different types of disease as well. In fact, that's what's done in some of the research I've mentioned before. But again, you have to think how much sense does it make from the problem that you're trying to solve.
Right.
And I guess just to briefly add that there might be advantage also of doing that in one single training, because you might learn models that better generalize. And that's something that we've also showed, and it's actually to appear in CVPR this summer. So watch out for that.
Oh, it's very interesting. Do you achieve better, I don't know, accuracy metrics using this multitask learning approach, or just better generalization?
Not so much the accuracy, because accuracy sometimes can be assigned that you offer fit to that specific data set from that specific lab, but you achieve generalization to data sets from different labs.
All right, very interesting. We have one more question. I assume that confounding requires special experiments to detect, I mean.
Yes, that's exactly the right point. The data that deep learning has mostly been applied to in medical domain is observational data from clinical, and it's not experimental data. And to really test what these researchers are claiming, we'd have to do experiments.
All right, that seems to be all of the questions currently asked. Really thank you, Evgeny. And
thanks a lot.
Now it's time to give the microphone to Povilas. There he's going to tell us about some causal inference approaches Povilas is working on algorithms in neurotechnology. The screen seems to be working all right.
Okay, probably you hear me.
Yeah, all good.
So my name is Povilas. I work at neurotechnology as algorithm researcher, currently with machine learning applications to electroencephalography data. Previously, I worked with adaptive robotics, and about 10 years ago, during my PhD studies, I had a wonderful internship at Max Planck Institute at Tübingen, where we worked on causality. So today I will try to talk about some maybe more theoretical approaches how to do causal inference. So the plan of presentation is the following: short introduction, some examples why causality is important, and then a few algorithms how to infer causality, and then some applications and final notes. So entire world actually is causal. If we think at various scales, we see causality everywhere. And it plays fundamental role not only in science, but in many other aspects, including our mind. And causal questions interested scientists and philosophers for many, many years. However, it is interesting to note that mathematical theories of causality were developed only in the 20th century. So here are prominent scientists who are like founding fathers of many fundamental algorithms, how to do causal inference. And correlation and statistical dependence in general is very often used to draw conclusions from data, and even current machine learning and deep learning is very much related to optimizing correlation-like measures. For example, in classifiers, we optimize cross-entropy loss, which can be seen as some form of correlation and so on. But it is easy to get incorrect conclusions from looking into correlations and misinterpreting that. Let's see into some examples. So we have a graph where we have two very strongly correlated samples. The red one is United States spending on science, space, and technology, and black one is suicides by hanging, strangulation, and suffocation. If we look causally into that, probably it maybe sounds paradoxical, but correlation coefficient is very large. Another interesting spurious correlation is divorce rate in men and per capita consumption of margarine. Also very strong correlation. Math doctorates awarded very strongly correlates with uranium stored in nuclear power plants, also quite decent correlation. And now the famous stork example. The data, I think, is from some region of Germany. And on x-axis, we have number of storks. And on y-axis, we have population. So if we misinterpret correlation, probably we can get a conclusion that maybe more storks deliver more babies to the population, and why it is increases when population of storks increases. However, correlation and causation are two different things, and those spurious correlation can be interpreted by Reichenbach common cause principle, which states that if two variables are statistically dependent, then there exists another variable that influences both of them. This variable z can coincide with x or I in special cases when there is direct causal relation. But in many other cases, including all cases we talked in previous slides, there is confounding variable z, which influences both variables. For example, if we go back to stork example, maybe there is like economic growth, and it influences growth of population, and people move to cities, and for storks appear many more space to reproduce, and consequently their population also grows. So according to Reichenbach common cause principle, such cases can be explained. So the question is how to mathematically handle estimation of causal direction from empirical observations. Let's say we have sample of pairs which are dependent, and we need to infer whether x is cause, I is effect, or vice versa, or there exists some variable z which confounds both other variables. So one of probably classical approaches, it is called additive noise model, and it uses the following idea. So let us assume following regression model. I is function from x plus some noise, and this noise is independent on x. Then inverse model, that x is another function from I plus another noise which is independent on I in this case, in general does not exist. So we can look at a very simple example. In the first column, we have sample xi, we have linear model, and in the bottom graph, we have noise plotted. So this noise, clearly distribution of this noise does not depend on x. And if we fit to the sample inverse model to regress x in terms of I, in this case, we have noise which depends on input. So this asymmetry can be exploited to infer which variable is cause and which one is effect. And additive noise model in practice works like that. We minimize dependence measure, for example, Kullback-Leibler dependence H6 or any other nonlinear dependence measure of input and error estimate in both sides. And afterwards, it checks statistical hypotheses about independence of input and error. And correspondingly, we can infer causal direction. So I also included link to code of that implementation of this model, if in the case if somebody would like to test by themselves. So another model I would like to talk about, not going to formalities, mathematical formalities too much, is information geometry causal inference, to which I also have a honor to contribute during internship. So in this case, we assume deterministic relation. I is function from X and F is monotonous nonlinear function as depicted in this graph. So hypothesis is that cause variable, in this case X, and data generating mechanism, which corresponds to function F, are likely to be independent. It is quite natural. And consequently, opposite is not true, because effect variable carries information both about function and about cause variable. So if we look into this graph, which illustrates this postulate, we have that slope of F. The first thing that we do not see any common regularities in input and in function. However, when input goes through the function, we have regularities which corresponds between regions of slope of this function and regions of larger density of effect variable. So mathematically, it can be reformulated that if this hypothesis holds, then input density or distribution should be uncorrelated with this variable. And if so, inverse model does not hold. So density of effect will be correlated with this variable where G is inverse function of F. In this case, F should be always monotonic function to this inverse exist. And in the case when the function is non-monotonic, the problem becomes trivial, obviously. So this also can be easily downloaded and tested on your data if you would like to do that. And let's go to another example. So assume we have access to collection of samples, xi, which are causally related. So the trick is vectorize those samples and just train binary classifier using supervised learning. And at least to time of publication, authors achieved very good state-of-the-art results. This model also can be downloaded and tested from GitHub. But what is interesting that with this article, learning-based approaches kicked in. So the rule is not based on some observation or some asymmetry, but just learned from data, as deep learning philosophy suggests. So another approach is like hypothetical idea. I tried to experiment with that few months ago, and it is related to the method we talked in previous slide. So the idea is do not use any training data sets, but to learn data generator from noise. So assuming additive noise model, we generate data and train classifier, which classifies causal direction. We know causal direction since we generate data by ourselves. But simultaneously, we can train generator as well to gradually generate data which is more hard to classify. So this principle completely corresponds to what is generative adversarial networks, but only applied to causal problem. And during the experiments, it often produced quite interesting and good results, but was very unstable, which is again is a property of generative adversarial networks. So I included this slide mainly because if somebody would like that idea, and you can write me and we can discuss it afterwards. So as Evgeny mentioned, there are many important applications of causal inference algorithms. Maybe the main reason is that so many things in their nature are causal. So in medicine, there is like treatment selection, how to select treatment which causes desired outcome, or how to design drugs which are efficient, for example, conditioned on genotype and so on. Another interesting application is in cosmology. It is based on half-sibling regression by Bernd Scholkopf, and it is used for exoplanet detection. So it learns to separate regularities which emit exoplanet which orbits some distant stars. So another interesting and very promising domain of causal inference is text data. Like, for example, if for human we give a story to read and ask causal questions, most likely we can answer them. And in machine learning and in causality, there is a version of a Turing test called the mini Turing test. So the idea is to feed the text to algorithm and ask causal questions and hope that it should answer as human. It is a restricted version of real Turing test, but it's still unsolved problem, and at least from not only from academic but also from commercial point of view, the inference in causal inference in textual data it seems to be very promising and important problem as well. So final notes, we talked about correlation, provide some funny examples about spurious correlation and how Reichenbach principle works, outline some different causal ideas like additive noise model, information geometry, causal inference, and two learning-based approaches. And note that causal inference indeed have many important applications, and I would add that it is very unexplored area of machine learning actually, and in the future, in my opinion, it will produce very interesting and maybe some groundbreaking results as well. So thank you for your attention, and if you have some questions, maybe I can try to answer them.
Right. Thank you, Povilas. Right now, I don't see any questions. I can only share that one listener is complimenting your slides. He says, beautiful Beamer slides.
Thank you.
Let's give a couple of seconds so people can write their questions if they have it. Maybe they're thinking about it right now.
We ask questions? Can I ask questions in the meantime?
Yeah, I think you go ahead.
I have a question regarding the method using GAN for causality estimation. I suppose the discriminator and the generator have to generate and take as input the whole data set at once, or several samples?
Generator, yes. Thing is that discriminator takes a sample as input, and samples can be of variable size. So, for example, there are methods which can be used for a discriminator like point-net or deep sets. So these are neural networks which work with such kind of data. They can take just point cloud or sample as input. And generator just, at least in my experiments, I use piecewise linear function generator. So the parameters of generator is some distribution in interval, and it constructs increasing piecewise linear function. And with piecewise functions, actually, we can approximate any continuous function. So seems sufficiently general thing.
Yep, sounds very cool. Thank you.
Thank you. Question.
Yeah, we have one question from Ruslanas. He says it's a great presentation, but if you can use GAN principle, probably you can also use variational autoencoder like probabilistic models for causality inference.
Probably, yes. I'm not sure how to do that in a few seconds, but somehow probably one ideas of one array can be transferred to algorithms in another branch. Need to came how to do that and then implement and see whether there is efficient, because can be that things which at a glance looks good in practice doesn't work, or vice versa, things that look not so elegant in practice can work very well.
Yeah, I think it's a great answer. I think it's probably a good idea if we gradually shift from just formula answering to like our panel discussion. So let's, if you have question for Evgeny or Povilas, or just general questions, you can go ahead and ask them in the chat. And I'm going to start with maybe like very simple question to kick it off. What are your favorite applications of causal inference and why? Evgeny, could you start first?
I'm sure I had in mind a favorite application of causal inference before starting this talk, but this session, but now it slipped away. I think what's been bothering, I can briefly talk about what's been bothering as an application of causal inference me recently is the, oh no, I do remember. The application of causal inference that I'm mostly curious about is the work of Esther Duflo. I believe I'm pronouncing the name correctly. She's a professor in econometrics at MIT, and she specializes in applying causal inference to policy decisions. In particular, the questions of what kind of areas to kind of solve the questions of poverty we should invest money in. And Esther Duflo works on designing experiments or working with observational data to answer these causal questions. Okay, where do we invest money to resolve global poverty? That's kind of very cool. And that's kind of emphasizes that the way of thinking, causal inference thinking, is widely applicable to all sorts of problems, from policy to medical imaging to astronomy, all sorts of things.
Yeah, very interesting answer. What about you, Povilas? How do you feel? What do you feel is your favorite?
I'm not sure that I have some existing favorite causal inference application, but what I would like to see that application of causal inference to modeling mind like application to artificial general intelligence, because the causal mechanism in our mind is very natural, and somehow this should transfer from causal inference methods to modeling of thinking process.
All right, that's a tall order, I guess, to get to AGI. But yeah, I mean, totally makes sense. I just recently myself found out that actually Jan LeCun and also Joshua Bengio both tweeted about causal inference. So Jan LeCun said that lots of people in machine learning and deep learning know that causal inference is an important way to improve generalization. And Joshua said that it's a big thing to integrate causality into AI. Current approaches to machine learning assume that the trained AI system will be applied on the same kind of data as the training data. In real life, it's not often the case. I just wanted to ask, what do you think about these tweets? What's your opinion? Maybe Evgeny, maybe you have some thoughts on that.
My first thoughts are that since you brought up Joshua Bengio, I want to put an advertisement out there that this summer we have a workshop, and Joshua Bengio's student, PhD student, who works on causal inference integration to AI, will be presenting at the workshop in Vilnius, Lithuania. So just putting it out there since we own it.
Yeah, that was totally unplanned, very natural.
Yeah, at least in my opinion, methods of causal inference probably can be used as like regularizers for regularization and in increase efficiency of other machine learning methods. Somehow those areas should merge in future and mutually benefit each other. And things that such stars as LeCun and Bengio are working and starting to work with causal methods, maybe just like message that this area starts to begin momentum in the highest levels of researchers.
I would just add to that also from like a different point of view, like besides Joshua and LeCun, there are like other researchers from industry organizations. If you think of Netflix or Google or Booking.com, where they have industrial questions, where they care about improving their products. And actually, if you look at the researchers who work at these organizations, they've been looking at causal inference for quite some time now and really building causal inference teams. Yeah. And that's kind of also very exciting. It's becoming more widely used.
And in Microsoft, I saw that it's like in Microsoft research, like causal inference group. So this thing becomes more popular actually. And there are even causal inference startups. I searched today a little bit. I'm not sure what they are doing actually, but a few years ago there were no such startups, I think, which specialize on causal inference.
That's actually a good point. A friend of mine works at Causal Lens in London, and we could bring them in to give a presentation here as well about what they're doing, since we brought up that question.
Yeah, very interesting. Do you have any thoughts on why is this happening right now? What changed in the world in the last couple of years that suddenly seems that causal inference is becoming important?
Maybe causal methods provide some explainability of machine learning. They are like more transparent, for example, and this correlates with various regulations and so on. There can be one of reasons.
I think another motivation also is, if we look from the medical point of view, okay, we have these very powerful function approximators now. We have clinical data, but actually just because we learn actions, mapping from features to actions from clinical data, we just learned the correlation, and researchers were kind of forced to start thinking about, okay, are these actions that we learned from observational data reliable? And there you have to move into the, at least from econometrics point of view, potential outcomes framework to start to think, okay, actually, how reliable are these models? And that motivates causal inference thinking once again.
It seems that people are pretty happy in the chat with our announcement regarding Witness Machine Learning Workshop. We also have one question from Ruslanos. Any specific, and I'm sorry if I'm misunderstanding it, but I'll read it verbatim, any specific amounts on difference between causal and predictive model concepts in your opinion? So how I interpret that is maybe you can like contrast the two approaches, the predictive approach and the causal approach in the from the model point of view.
Well, predictive it is not necessarily causal, I would say, if I understand correctly what by predictive means.
Maybe it's worth to think of the example that I've shown for the two regressions, gene A and gene B. And if we are in simply predictive domain where we just learn a linear regression, and if gene activation is at 0, then we would expect the phenotype to be at 0 as well. But if we're in the causal domain and we know that there is a common confounder, then that relationship might not necessarily be linear anymore. In fact, there is no direct relationship. And being in the causal domain would force you to think about that.
Yeah, actually, that's a very interesting avenue to talk about. I'm very interested in, do you know any cases where somebody ignored causality and it didn't end well? I mean, for practical products, maybe somebody just, we just slap a predictive model and it's gonna go. This amazing deep neural network will just get 95% accuracy, and it's all that we need. Yeah, Evgeny, I see that you had.
Well, now that you've mentioned more, I understood it's a more recent example, but often if you listen to, for example, Jonas Peters' lectures, this is one of the authors that Povilas mentioned in his slides. He brings up the example of smoking. And this was a big debate a few tens of decades ago when people tried to determine, does smoking cause cancer? And that was exactly the question of predictive versus causal question. And it took several, because the causality as a research field was still evolving over that time, as this debate over smoking was happening, you could see at the same time causal methods evolving until multiple publications led to us finally concluding that smoking causes cancer. And causality played a big role in that as well.
Right, yeah, very, very interesting. I guess very interesting example. I always remember in one of the statistics books there was an example that ice cream consumption causes drownings. That obviously there might have been a confounding variable in this case, such as summer. Povilas, do you have any I don't know, cases where their causal models there the right way and somebody just didn't know that they should be using that and yeah, then the project failed because of that, or like we made incorrect predictions?
Hard to remember actually such cases, because actually I don't think about causality so much. Only have this good opportunity to remember things. So probably maybe later somehow I can answer this question.
Actually, if I may, I actually think there is a confounder in this question, because your question is very much time dependent. And I think causality, we're only starting to think about it very recently. It's becoming popular. So we will only start to see more, it's like a survivorship sort of bias that's only starts to kick in. We will only start to think of the problems now, the community in different scientific fields and applications fields, that actually no, causality did matter here. And one thing you can think of is recommendation systems. For the most part, recommender systems like collaborative filtering were based on just correlation, right? We just learn a dot product of different features between different customers, which is correlation in some sense. And if we train that on historical data, we're actually just training on correlation, but we don't necessarily know if we serve that particular product, or if we served a different set of products to the customer, how would have they responded? And it's a counterfactual kind of question that is very much a causal inference question. And only in the recent few years, you can see people publishing literature and companies starting to think of, okay, how do we build recommender systems from causal inference point of view? And Netflix has quite a bit of work on that. There was an interesting, since we talked about GAN's paper in last year's NeurIPS, where they actually tried to build a very similar idea to what was mentioned before in the presentation. The two recommender systems, and one recommender systems tried to predict the counterfactuals of the other system, and it becomes a very interesting problem. But also, probably, if you're trying to train it, it's extremely unstable as well.
Probably, and good recommender system, probably the criterion in practice is that it should bring money.
Mm-hmm.
So from causal point of view, it is, of course, interesting problem, but maybe some reinforcement learning algorithms would help more to design the cost function, which or reward function, which accumulates like amount of profit.
But then you get to the whole idea with reinforcement learning. You have historical predictions from reinforcement learning, and then you try to evaluate a different version of that.
Yeah,
and you can't. And it's a counterfactual question.
Yeah.
I'd like to step back a little bit. You mentioned that during the smoking debate caused a lot of development in the causal inference field. And maybe you have, I don't know, ideas on how causality will evolve, and what can it, how can it be beneficial to artificial intelligence and vice versa? What new problems we are going to have, what new solutions, and other things we are going to have here.
At least in my opinion, causality should absorb deep neural network machinery to make more data efficient, to exploit just data into more efficient inference engines. One of possible directions.
One interesting thing that I've been thinking about is there is a package from Microsoft as well. I think it's called DoY. The way this package works, DoY, is that you provide a causal graph to the package, and then using Pearl's do calculus, it infers what are the right ways to then estimate the causal effect that you're interested in. So either using backdoor or front door criterion, or whichever you're interested in. Actually, if you think about it, about that package and the steps that it does from a meta learning point of view, I was wondering, kind of very abstractly thinking, if you can, for example, write that whole package in Julia, let's say, and then have a neural network controller to then apply this set of tools that you have in DoWhy to different sets of problems. And then you can sort of meta-learn a causal inference data scientist, sort of in a spirit of automatic statistician from Zubin Harmani. That's also sounded super interesting. And as we see more meta-learning approaching, maybe we'll see that one day.
Yeah, meta-learning is also the area which should integrate into causality, and integrates. Even some time ago, I saw articles which combine meta-learning and causal inference. So.
Yeah, super cool.
All right. I was just wondering, Evgeny, how do you spell the package?
Oh, it's DoWhy. It's literally do, like D-O and Y, like question of why. It's a play on, I think, on Pearl's Do Calculus and his book of why.
Okay. Yeah, thank you. Let's see if we have any. Oh, Ruslana says that Evgeny made a causal joke. I guess that was a bit some time ago. Maybe I have one more question. How do you view a potential of academic and business cooperation in the, like, I don't know, research of causal inference algorithms? You mentioned that Netflix is investing in that. Obviously, Microsoft is investing in that. How do you feel this might develop in the future?
So need bridge building, like to find profitable applications and which would stimulate researchers. The same, I think, should be the same story as with neural networks.
Yeah, maybe actually that's a very good point. Because as Pavel has mentioned, we in deep learning we had ImageNet, and ImageNet sparked applications. With causal inference, what you see, it seems now, you have different research groups like islands. You have Bernard Skov group working on that, a few other research groups, and then you have special kind of industry organizations, Microsoft, Netflix, who run a lot of A/B tests and other observational studies, and they have to develop these methods and improve these methods.
Yeah.
But the problem is that these data sets are not available where you can test. There are very few real challenging data sets like ImageNet scale for causal inference.
Yeah, there is too big on cause effect pairs, but at this time it is too small. Actually, it should be 1,000 times larger.
So yeah, probably data sets from my point of view is what's needed. Public data sets always, then researchers jump on public data sets.
All right. Yeah, let me check if we have any more questions. We don't seem to have any more questions. I think it's a great discussion. Do you have anything, any last ideas, thoughts to add to the discussion?
Not really.
What about you, Paulius?
I too join this opinion.
Right. So it was a real pleasure having you here today. I hope that this is definitely not very common theme right now, in at least in my circles. And I really hope that people learned what is causal inference, why is it important, how it can be used, and even some examples of like what you presented, some use cases, and how it's actually being used even right now in to solve practical problems in various fields. So it was really great having you here today, and see you all next time in our next artificial intelligence meetup. Bye until then.
Bye-bye.